Okay, the next lecture is conservation of momentum in two dimensions. This is section 5.5 in your textbook. So we jump a little bit ahead. The types of collisions that you can use conservation of momentum in two dimensions for are often referred to as glancing collisions. So these are collisions where we have a very small delta t, a time of impact, and where we can kind of ignore the friction before and after the collision. So your textbook is really good in terms of explaining this section well. So make sure you do read section 5.5. But I will go through this lecture and I'll go through some of the problems. You'll see it's pretty short here because we've talked about the main issues in conservation of momentum in the previous lectures. So when we have collisions in two dimensions, it's the same concept of conservation of momentum. You would have remember in the conservation of momentum lecture, I talked about how the conservation of momentum is independently conserved in each dimension. So that means our row x and our row y before and after are the same. Or you can say that the change in momentum before and the change in momentum after is 0. This is an example actually from your textbook. So because your textbook goes through this, I won't go through this problem, but I will talk about it a bit. So we have two cross-country skiers, and they're not paying attention to where they're going. One is going east, one is going directly north, and they hit each other. When they hit each other, they become entangled, and they can be treated as one mass, one object, and they have a final velocity at some angle in that northeast quadrant. So in order to find this, we know that their x momentum has to be 0. So the momentum of the skier who's going to the east has to be conserved. The momentum of the skier who's going to the north, that momentum has to be conserved. So as you kind of calculate this, and if you follow the textbook example on page 251, you'll see that it will involve having an x component to the momentum after and a y component to the momentum after. You'll have to find the sum of the vectors. So you'll have to do vector addition using a Pythagorean theorem. You'll find the magnitude, and then using the inverse tan, you can find the angle. And I prefer, again, that your angles, you always write your angle as whatever is less than 45 degrees. So your answer should be 3.6 meters per second east, 41 degrees north. Although your textbook does say it's 3.6 meters per second north, 49 degrees east. I would just prefer you write the smaller of the dimensions or the angles. Although you'll be marked correct either way. That's not really a that's not really a standard convention. So let's look at this problem here. It says a billiard ball of mass 0.15 kilograms is rolling north at 3.5 meters per second, and it collides with a stationary golf ball of mass 0.5 or 0.05. It says the billiard ball rolls off at an angle of 15 degrees with a velocity of 3.1 meters per second. What is the final velocity of the golf ball? So I'll show you how to do this quickly. So here are our givens for this problem. I've used lowercase b for the billiard ball and lowercase g for the golf ball. So here's the masses of both objects, two significant digits. Here's the velocity of b before. It's totally in the north direction. The velocity of b after is north with an eastward component. The velocity of the golf ball before is 0 because it's stationary, and we're asked to find the velocity of the golf ball after. So what we'll do here, and it doesn't matter which one we start with, but we'll start with x. We'll find out the momentum of x before and after. So our I'll write out everything and then I'll start canceling things out. So VMB VBX plus MG VGX equals MB VBX prime plus MG VGX prime. What I know is that my golf ball before is going directly to the north. So this is 0. I also know that my my billiard ball is going directly to the north, so that's 0. My golf ball has no movement, it is stationary, so this is also 0. Afterwards, I will have a component of in both. So these are both going to be non-zero values. And because I need to solve for VG prime, I need to solve for VGX prime here. So my VGX prime is equal to negative MB over MG. So that was negative MB over MG VBX prime. And I know my VBX prime from this. So I can actually continue to calculate this. So let's see. VGX prime is equal to negative 0.15 over 0.050. And then it's 3.1. So I have to do, it's 15 degrees, so it's kind of like 15 degrees off this way. So to find out my my x component, I'd have to do the sine of 15. That will give me my x component of this value. And my VGX then should be, just a second here. So 0.15, I'll remember the negative and I'll just add it in after. 0.5 times 3.1 times 15 sine. So it should be negative 2.407. And that's meters per second. I'll just leave it like this because I don't need this. This is not my solution. This is what I'm going to need for part of my solution. So this negative is telling me that it's going to be going to the west. Now I can find my momentum in the y after and my momentum in the y before. So again, writing this out, MB VB y plus MG VG y. You won't have to write this out every time. I'm doing it just to teach you how to do these problems now. But I recommend you do write them out until you start to get a full understanding of how to do these problems. So here my y is non-zero, but here my VGY is 0 because I have a stationary golf ball. Afterwards, I'm going to have non-zero values. And again, I have to solve for VGY prime. So isolating for VGY prime, that's this value here, I'm going to have 1 over mg. I can factor out the mb, so I'm going to have mb over mg. And then it will be VBY minus VBY prime. So I know that I can calculate this, or rather this from my, for using cosine of 15 from my initial here, or rather my final that is given to me. So my VGY prime is going to be MB, which is 0.15 over 0.050. VBY was initially 3.5 in the north, so I'll take that north as positive. I'm going to the north here, so I'll take that as positive. So this is going to be minus 3.1 cosine of 15 degrees. And calculating this, and I calculator gets me to 0.15 divided by 0.05. So that's 3. So 3 multiplied by bracket 3.5 minus 3.1, sorry, 3.1 times 15 cosine. I get a VGY of 1.517 meters per second. I'm taking a few extra variables back here because I need to consider that this is only a part of my solution. This isn't my final solution. And this tells me that my VGY prime, my golf ball, is going to be going up and to the left, or north and to the west in this case. So now I have to find out what this will actually look like. So my final momentum, or my final velocity of this golf ball is going to be an addition of VGY prime, that's the upward direction, and VGX prime. So this value and that value, which is down here, I will now use those to find out what my VG prime is, my final VG, which is going to be VG prime equals, so the square root of VGX prime plus VGY prime. So the square root of 2.4, sorry, these are squared as well. So this prime squared. So 2.407 squared plus 1.517 squared, and the square root of that. I already have this value in here, so I can square this, plus 2.407. That's enough significant digits in order to do this intermediate calculation, so we're fine with that. The sum of those is 8.09. I find the square root of that sum. I end up with 2.845. And when I round for significant figures, that will be 2.8. But before I do that, I need to do one last calculation because I need to find out what is this angle. And that angle is the inverse tangent of VGX prime over VGY prime. So the inverse tangent of VGX, which is 2.407 over 1.517. That is, so 2.407 divided by 1.517. I find the inverse tangent of that. I end up with a 58 degrees. And because, as I was saying, I like to always put these as values that are less than 45 degrees. So what I should have done, I think I mentioned this previously, is you should always put the lower value on top to find out what that angle would be. But what I can easily do now is just do 90 minus 58 to find out what my other angle would be. It would be 32 degrees. That's my complementary angle. And that then gives me my my VG prime, which I'm going to report as 2.8 meters per second. I am going to be going more towards the west. So it'll be west, 32 degrees, north. That is my solution to this one. So let me go back. I'm going to do one more problem in this lecture. And this one's actually one we can just kind of talk about. So here we have two cars. They have an identical mass. They're approaching the same intersection. One comes from the south, one comes from the west. So the one from the south is going north, one from the west is going east. It says they lock together and they move away at an angle of 55 degrees. So which car was traveling faster than the other before the collision? So considering that the masses are the same for both, in order for the cars to collide and tilt more towards the direction that MA was traveling, VA must have been greater than VB, because there must have been a greater momentum for MA in order to have the final condition be pushed more in that direction. You can prove this mathematically. I won't go through that, though. It's rather simple. So I would recommend, again, read through this entire section in the textbook 5.5. I know it seems like we skipped a little bit, but I think it's important to do conservation of momentum a little bit more before we get into a greater analysis of collisions.